So now we're going to begin our study of chemical kinetics. Chemical kinetics is simply the study of how fast reactions go, or reaction rates. It's a study of the rate of reactions and the factors that influence how fast they go. And these factors include four major features. The first is the nature of the reactants, what kind of molecules they are and how reactive they are. The second is how much of the reactants there are, the concentration of the reactants. The more concentrated reactants are in general, the more opportunities they're going to have to bump into each other and potentially the more opportunities to react. Another big influencing factor is temperature. Okay, and the rule of thumb generally is that the higher the temperature, the faster your molecules are moving. So the more often they're going to collide and the faster the reaction is going to go. So the higher the temperature, the faster the reaction rate. And the final influencing factor for reaction rate is catalytic effects. Catalysts are agents that speed up reactions. Catalysts can be biological. Enzymes are biological catalysts. So, enzymes are large proteins that make reactions go faster. Catalysts can also be just small chemicals, small molecules that make reactions go faster. So, abiotic catalysts as well. So we're going to talk about all of these various influencing factors in our discussion of chemical kinetics. But before we do that, I'm going to give you an introduction to reaction rates and what that means. So let's consider a very simple case to start out with. In the simplest case where reactant A goes to product B, okay, these are just fake reactants and products. The reaction rate simply tells us how the concentrations of each species, both the reactant and the product, A and B, change with time. So a way of writing that mathematically is to define the rate of reaction as how the concentration of each species is going to change per unit of time. The units of that would be units of concentration, which are moles per liter, over units of time, which are seconds. So the units would be moles per liter per second, for example. Now, we're talking about reactant A and product B in this very simple example. So you start off with reactant A, and over time, you're going to have some change in the concentration of A. So that little delta means a change in the concentration of A. Since A is the reactant, it's going to be decreasing in concentration. So I'm going to put a negative sign there. And we can measure the change in the concentration of A per unit of time, which I'm going to call delta T, where I am just dealing with a small chunk of time. So this negative sign here, the negative sign is indicating the loss of reactant A. So conversely, when we think about product B, we're going to have a positive sign. So while A is decreasing, B is going to be increasing. So we have a positive delta B to symbolize the gain in product B. So I wrote these with delta, but another way to write this is using a lowercase letter d. So sometimes you see dA over dt, where d just symbolizes that delta, that change. So this is just another way to write that same thing. A change in A over a small chunk of time, delta t. A change in B over a small chunk of time, delta t. Okay, so we can write the rates of the reaction like this. All right, so let's think about how we can show rates of reaction graphically. Now, one thing that is maybe intuitively obvious, I hope, rates of reactions are not usually constant. So rates of reactions are not usually constant. They're going to decrease as equilibrium approaches. Let me show you what I mean. Here I have two axes, and on the first axis, I'm going to put the concentration of reactant A. Whenever I put something in brackets, those brackets mean the concentration of whatever is inside the brackets. So let's look at the concentration of reactant A as a function of time, and the concentration of product B also as a function of time. So we start out with a lot of product, right? So I'm going to start off with A kind of up here at the top. Now, as time goes on, the concentration of A is going to decrease, but it doesn't do so in a constant way, right? You can see that we have a bit of a curve here, reflecting the fact that the reaction rate is not usually constant. Same goes for product B. I start out with very little or none of product B, and as the time goes by, the concentration of B is going to increase as reactant A is converted to product B. So you notice that the curve of B is the mirror image of the curve of A, essentially. Now, let's look at a little chunk of time. I'm going to use my little graph paper here called delta T. And I want to compare delta T at the beginning of the reaction and then towards the end of the reaction over here. And I want to do that for both the reactant A and the product B. So I'm just looking at chunks of time called delta T. Okay, so looking here, if I kind of follow this all the way up, I can see that if I compare the beginning of the reaction with the end of the reaction, the delta A per chunk delta T is going to be much larger at the beginning of the reaction than it is at the end of the reaction. Okay, so here I'm just kind of going over here, but you can see that this delta A is much bigger than this delta A down here. Same goes for delta B. Okay, here at the beginning of the reaction, the delta B is much greater than it is here at the end of the reaction. Okay, of course, I'm freehanding this, so this is not a perfect illustration, but you can see that this dB up here is much smaller than this dB down here. So this is showing that the rate of the reaction, whether we're considering it from the point of view of the reactant or the point of view of the product, the rate is going to be greatest at the beginning of the reaction. And I hope that makes sense, right? Because if we have a reaction that's going in just one direction, at the beginning you have lots of reactant colliding and converting into product. And as the reaction proceeds, you have fewer reactant molecules. So the reaction rate is going to start to slow down, okay? But the curves here show you that for each chunk of time, delta T, the change in A or the change in B, dA or dB are going to be different. So reaction rates are not constant. Reaction rates decrease as equilibrium is approached. So what else can we say about this? Well, I've been implying so far that reaction rate depends on concentration. And this is not always true, but it's quite often true. I'm going to give you an example. Let's take a reaction where dinitrogen pentoxide decomposes to produce nitrogen dioxide and oxygen gas. So here we have the balanced reaction. 2N2O5 gives 4 NO2s plus 1 O2. So experimentally, if you do an experiment on this reaction, we observe that the concentration of dinitrogen pentoxide, if that is halved, so if we cut this concentration in half, so is the rate of the reaction. Okay, so if we cut the concentration in half, we cut the rate of the reaction in half too. So that experimental observation tells us that the concentration of N2O5 and the reaction rate are going to be directly related to each other, directly proportional to each other, because if we cut one in half, we cut the other in half. So a way of expressing that is by using the proportionality fish. The rate is proportional to the concentration of that reactant, dinitrogen pentoxide. Now, if we want to convert that proportional statement to an equation, we get what's called the rate law. The rate is equal to some constant, I'm just going to call it K, times N2O5. And all that does is it takes this proportionality, and by multiplying it by an actual constant that I'm going to call K, we can change that proportionality fish to an equal sign. So K is very important. K is a special constant called the specific rate constant. This specific rate constant depends on temperature, and it depends on the nature of the reaction. Now, how do you get K? You have to use experimental data for a particular reaction if you want to calculate K. So let's take the experimental data for this reaction where dinitrogen pentoxide decomposes to nitrogen dioxide and oxygen. So 3 experiments were performed, 1, 2, and 3. And these experiments were performed with different initial concentrations of dinitrogen pentoxide. So these are the 3 different initial concentrations that were used for the 3 trials. Each of those experiments gave a different rate, okay? So you can kind of see that the higher the initial concentration, the faster the rate. Now, let's go back to the rate law for a second. The rate law for this reaction is that the rate is equal to K times the concentration of dinitrogen pentoxide. So you can calculate K by rearranging the rate law. K is going to be equal to the rate divided by the concentration of dinitrogen pentoxide. And if you do that in each of these instances, you can fill in the values for the specific rate constant. So 0.035 divided by 0.1 is going to be 0.35. And the units here are seconds to the -1 because the concentration units cancel. 0.07 divided by 0.2 is also 0.35. And 0.14 divided by 0.4 is also 0.35. So you can see from this data set that K is constant. Now, of course, K is a specific rate constant, and K should be constant provided that all reactions are happening at the same temperature. Okay, so you have to use experimental data if you want to calculate K, and you can get it from the rate law as we showed in this example.